Hi, in this video I'm going to continue talking about first order systems. The last video talked about a simple water tank model as a first order system. In this case we're going to look at a resistor capacitor circuit as a first order system. So this is the circuit here below. It has an input, an output, that's an input voltage and an output voltage. It also has a resistor and a capacitor. That's the entire circuit. Okay, and the resistor has a resistance of R and the capacitor has a capacitance of C. What we'd like to know is how the voltage V0 changes with V1. So let's say we were to increase V1 say to 5 volts. So what that would do is the current would start flowing through I, and it would start charging the capacitor. Now I'm going to assume that the current flowing out here is 0. Okay, so the current flows from the resistor and starts charging the capacitor. As a result, the voltage V0 will start to change. So what we're really after is dV0 by dt, and somehow that's a function of the input voltage. So that's what the relationship we'd like to know. Okay, so how are we going to do that? Well, we're going to have to invoke some basic laws of electricity. The first one is Kirchhoff's voltage law. Okay, and all that says is that in a loop the sum of the voltages must be 0. Okay, so let me get rid of that. So the sum of the voltages must be 0. So here's the loop here. There's a loop in there, okay? And so the three voltages, there are three voltages here. There is V1, V0, because that's what's across here. And then this voltage here, VR, which is across the resistor. All right? Okay, so I can write down then Kirchhoff's law as this, voltage law, V1 plus VR plus V0 equals 0. Okay, I can rearrange that to get this. Alright, so the V1 is just the sum of the voltage across the resistor and the voltage across the capacitor. Now the other thing we know is what the voltage is across the resistor. We know that from Ohm's law. Okay, so I can invoke Ohm's law for the resistor so that the voltage across the resistor is equal to the resistance times the current. Right, so these are the two basic relationships we've got, and here they are. I just repeat them here. Okay, Kirchhoff's law and Ohm's law. Now the other thing we know, which I mentioned last time, is that when we increase the voltage on V1, the current starts to increase, and the current has only one place to flow or to go, and that is into the capacitor. Right? So the current actually that's charging the capacitor is the same as the current going through the resistor. Right? So I know that this current and this current are the same. All right, that's an important thing to know. So I just repeat these equations here and here. Alright, and the fact that this current here is the same as this current here. We know one other thing, and it's the only other thing we need to know, is the relationship between voltage and current in a capacitor. And this is the relationship here. Okay, this is I don't know, you could call this the capacitor law. So it says that the current is equal to the capacitance of the capacitor times the rate of change of the voltage. Now we can insert this I into here, and so I end up with this. Okay, I end up with that. Alright, so I have the relationship now between the rate of change of the voltage RC and the voltage across the resistor. Now I'd like to get rid of this voltage. I'd like to get rid of that somehow, so that's the next thing we're going to do. So that turns out to be quite easy. All I have to invoke is the Kirchhoff voltage law, which we did in the first time. This is the equation I just had in the last slide. course, I can now substitute this into there, so I end up with this. Okay, that's basically the answer we were after. I can rearrange it so we have rate of change of voltage on one side, so I get that. Okay. Now sometimes you might see people writing it either like this, or they might write it like dv0 over dt equals 1 over rc v1 minus v0. Right? You'll see it in various forms. Right? And this is a first order equation, or first order differential equation. So the big question is, so why is this first order? Right, so this is the equation we just had from the earlier slide. Why is that a first order equation? Well, it's first order because the rate of change on the left hand side, this side here, is only the first derivative. Okay, it's only the first derivative. There are no higher derivatives. Okay, let's do that differently. There are no higher derivatives. And of course, it's only a single differential equation, meaning there's only a single variable in our system. So that tells us this is a first order system. Okay, thanks.